Good morning. Our project deals with design and development of heat flux gauge. The team consists of Abhishek S.Saraf, Rajesh Nair M, and myself, Vhyvhitavya V.V.S.J.A.R. Our project was successfully carried out at CSIR NAL Laboratories, Bangalore. We have carried out the project work under the guidance of Professor S.V. Subbarao internally and Mr. C. Jayaprakash at the site. This is our team. Our objective was to develop a cost-effective heat flux gauge which can be employed in high temperature transient heating conditions. Thermal sensors play a vital role in the design, development and qualification of thermal systems and subsystems. Apart from conventional sensors for measuring heat, fluid or wall temperatures, of late measurement of heat flux has become very common. A variety of techniques, both intrusive and non-intrusive, have been developed for the measurement of heat flux, flame and surface temperatures are used by scientists in aerospace field. With advances made in aerospace industry, high temperature and high heat flux measurements assume a great importance. Heat flux is the amount of heat transferred per unit area per unit time from or to a surface. It involves two quantities, the amount of heat transfer per unit time and the area from or to which the heat transfer takes place. The devices that measure heat flux are called heat flux gauges. The various types of heat flux gauges are slug type, thin foil type, thin film type, thermopile type. Low temperature heat flux gauges such as the ones which are used for water boilers are already available commercially. High temperature heat flux gauges have to be manufactured since their usage is restricted to materials under high temperatures. This project deals with slug type heat flux gauge for high temperature applications. Slug type gauge consists of a metallic disc of known mass, usually of high thermal conductivity material, which is thermally insulated to reduce the heat loss, and one or two thermocouples attached to its rear surface. Rate of rise of slug temperature is proportional to the rate of heat transfer to the slug. This type of gauge is extremely useful in solving a number of thermal problems and also as a diagnostic tool in the propulsion area, especially where the total test time is in the order of milliseconds and the heating rates are high. It also finds wide application where the size limitations do not allow the use of other gauges or when it is not feasible to provide cooling. Copper is chosen as a slug material as it has high thermal conductivity. Its melting point is 1356 Kelvin. A K-type chromel-alumel thermocouple is attached to the rear end of the copper slug. It can effectively measure temperature of 1523 Kelvin. The copper slug along with the thermocouple is embedded into an alumina-based ceramic insulation which can withstand a maximum temperature of 2073 Kelvin. One end of the thermocouple is attached to the copper slug via brazing or adhesive cement bonding, and the other end is connected to the one channel of data acquisition system. This is the formula which has been used. The theoretical calculations were done using forced convection and radiation formulae. Theoretical heat flux value for 3 mm copper slug is 100.2 kilowatt per meter square and 6 mm copper slug is 235.4 kilowatt per meter square for the temperature difference of 263 Kelvin. Based on theoretical calculations, the dimensions of copper slug and the ceramic insulation were decided to the above parameters. The first photo shows the 3 mm and 6 mm copper slugs. Second photo, the thermocouple with brazed copper slug. Third photo, the ceramic insulation used, and the fourth slide is the total heat flux gauge. The experimental setup consisted of gas cutting, oxyacetylene apparatus. The upstream and downstream hose pressures of both cylinders are adjusted as per experimental requirements. A holding device for flame torch is set up, and a movable holding device for gauge is also set up. The gases are ignited and the flame is adjusted for low, medium and high flow rate settings. The central axis of both flame torch nozzle and the copper slug are aligned perpendicular to each other. The thermocouple is connected to the data acquisition system and continuous data is logged. The slide shows the experimental procedures at various times. These are the graphs that were obtained after compiling the data from DAS. Heat flux and temperature are plotted against the time. Note that wherever there is a temperature difference, there will be a heat flux difference. First graph is for 6 mm copper slug. Second graph for 3 mm copper slug. Fourth one for 3 mm copper slug. Fourth graph is for the copper slug which had been experimented with the solder gun. Since we didn't have any referential gauge, we have compared the compiled data with this solder gun experiment, and the results are as shown. We have compared the data that was logged during the gas flame experiment and the data that was logged in during the soldering rod experiment at lower temperature and higher temperature differences respectively. Here we can say that the variation of heat flux is almost negligible in the given temperature band. It has been experimentally shown that the output of a single thermocouple placed at the rear surface of the copper slug can yield sufficiently accurate measurements of varying high heat fluxes in the range of 50 kW per meter square to 250 kW per meter square. Results achieved by this method are in agreement to 10 to 15% of numerical calculation results. Since the time response is determined by the length of the slug and the thermal diffusivity, which varies with the temperature, the gauge response is temperature dependent, and therefore the relevant material and size must be defined upon test conditions and experimental requirements. The slug type heat flux gauge developed can be tested in high speed and high temperature flows, or also in real world conditions like combustors. It simplifies the data acquisition, particularly in flight applications, thermal shields requiring a large number of calorimeters under very high heat fluxes, thus enabling it for wide application in the aerospace field. Thank you.